Okay, so we are going to spend the next couple of weeks working on the same topic, which is complex numbers. This is a topic that we aren't going to see in the parent class until section 10.5. But because there's a pretty good amount of prerequisite stuff to talk about with the complex numbers, I want to be able to give us time to stretch it out over these 2 weeks. So this week we're going to focus on the arithmetic and a little bit of algebra with the complex numbers. And then next week, we're going to focus on the geometry of the complex numbers. But to begin with, we need to talk about what complex numbers are in the first place. So complex numbers begin with something that we call the imaginary constant. Imaginary constant. The imaginary constant is this number that we refer to as I. And oftentimes we're taught that I is the square root of -1. Or another way of saying that is I is the number that we can square to equal -1. You first learn about this number I in intermediate algebra, typically. And initially it seems like it's something that shouldn't exist, hence the name imaginary. We're taught early on when we first learn about square roots that we can't take square roots of negative numbers, because anytime you square a real number, the answer is always non-negative, either 0 or something that's positive. However, there's a lot of applications, a lot of areas of math where we are kind of stuck if we can't come up with some way of dealing with the square root of a negative number. So we sort of invented this number I. And just to sort of quickly discuss that, a lot of people take issue with the fact that we can just invent a number like this. It seems counterintuitive. After all, numbers are often taught in a way that feels very natural, like in sync with the world around us. You know, we can imagine whole numbers as representing discrete quantities. You know, I have 5 apples. You know, that's a very easy way of understanding whole numbers. Fractions also have very, intuitive interpretations, things like that. But if you go far enough in math and you study what we call the foundations of mathematics, you actually learn what to some people is kind of an unsettling truth, which is that literally everything in math is invented. The number 1 is invented. Even though it describes something that is very easy to imagine, it's no less it's no more of a real quantity than this number I is. So we do this kind of thing in math all the time. But when you first see this thing, about imaginary numbers and complex numbers, it seems very counterintuitive. So we're just going to accept that this is okay to do in math, that we can invent this number I, and it's defined by this property. So let's go ahead and move on with this concept. What I want to start with is using the 4 basic operations with what we call complex numbers. So now that we've defined this number I, what is a complex number? Well, a complex number is any number of the form A plus BI, where A and B are real, meaning real numbers, okay? Real numbers are the set of all numbers that you are already familiar with. Positive, negative, rational, irrational, doesn't matter. Those are all real numbers. Complex numbers look like expressions that have this form. So let's look at some examples. The number 3 plus 4i. That's what we call a complex number. We kind of think of this I here almost as if it were an x. If I had 3 plus 4x, I can't combine those because they're not like terms. So there's no simpler way of writing this number 3 plus 4i. We refer to the 3 as the real part and the 4 as the imaginary part. Another example of a complex number, -1 minus 6i. It's not a problem that this is a minus instead of a plus, like the definition says, because I could alternatively write this as -1 plus -6i. I just think of the imaginary part as -6. This is an imaginary number. 5i. In this case, the a that's appearing at the beginning is a 0. You don't see it, but I could have written 0 plus 5i. Similarly, and this is kind of the more interesting thing, all real numbers are also complex numbers. So if I take a look at, say, the number 10, that's a real number, but it's also a complex number because the imaginary part, the b, of this complex number would just be 0. I could say that this is the same as 10 plus 0i. 0 times anything including I is just 0, so that just simplifies down to 10. So basically, complex numbers represent a larger set of numbers containing all of the numbers we already know, but also containing all other numbers that take this form. So let's talk about the arithmetic with the complex numbers: addition, subtraction, multiplication, and division. Addition and subtraction are really easy with complex numbers because we treat the I in a complex number as if it were an x, some kind of expression with a variable. So for example, if I wanted to do 3 plus 10i, that's one of my complex numbers, plus, let's say, -7 minus 4i. I'm adding two complex numbers, but really what I do is I treat it as combining like terms. The two real parts are like constants. 3 plus -7, that's -4. The i's are like, we treat them like x's. 10x minus 4x would be 6x, only here I would call it 6i. Really straightforward. Same thing with subtraction. We treat it just like we would an algebraic expression. So if I wanted to do, let's say, 5 minus I minus 6 minus I. Well, in this case, what I would do, just like I do in algebra, I would distribute the minus into the second set of parentheses. 5 minus I minus 6 plus I. Okay, in this case, notice that the negative I and the positive I, those end up canceling out. 5 and -6 combine to make a -1. And in this case, the I appears to just go away. But again, remember, this is still a complex number. So that's there's no real point in doing more examples of addition subtraction. It's just like dealing with combining like terms. Multiplication and division are where things get a little bit more interesting. It's where we actually need to use the definition of that imaginary constant I. So let's take a look at a multiplication problem. Let's say I wanted to do 2 plus I times 3 plus, let's say, 5i. Okay. At the beginning, this also looks just like a regular multiplication of two binomials from algebra. We can use FOIL. So first, outside, inside, last. If I do that, I'm going to get 2 times 3, that's 6. 2 times 5i, that's plus 10i. I times 3, that's 3i. And then I times 5i would be plus 5i squared. So far, this doesn't feel any different from a regular multiplication of binomials from algebra. Where things change, though, is this I squared right here, because we know by definition I squared is equal to -1. So anywhere where an I squared appears, I can change that into a -1. So this will become 6 plus, I can also combine these terms, 10i plus 3i would be 13i. This I squared becomes -1, which then multiplies to that 5, making it a -5. And what I end up with is 1 plus 13i after combining those like terms. Okay? So that's essentially what happens with multiplication. If you're multiplying two complex numbers, and if each one has an I present, then you're going to end up with an I squared. That becomes a -1, which we then use to simplify. At the end, this thing should look like a complex number, a plus bi. And remember, either the a or the b can be 0, and we wouldn't really write that, but it still could be thought of as being in that form. A couple of things I want to look at with complex numbers. And multiplication in particular. One is, what if we square a complex number? So if I have 1 plus I squared, I could raise it to any power really, but let's look at 1 plus I squared. Well, remember this is the same thing as 1 plus I times 1 plus I. And so we would still treat this like FOIL. I point this example out because I don't want you to fall into that trap that a lot of beginning algebra students fall into of thinking that you could distribute that too. You can't do that. It's this, right? Now if I did FOIL on this, I'm going to get 1 plus I plus I squared. We know that that I squared is going to become a -1. So I have I plus I, which is 2I, minus 1. Notice the 1 and the -1 cancel out, and all I'm left with is 2I, right? Go put a box around that one too. All right, so you'll have to do a little bit of that in the assignment for this week. But one more multiplication example I want to look at, and this is actually the most important one because this is going to become something that we also use for division. What if I were to multiply two numbers that look like this? Let's say 3 plus 7I times 3 minus 7I. So you'll notice that the two complex numbers that I'm multiplying together look very similar, but the only difference is that I have a plus in one case where I have a minus in the other case. We call complex numbers that have this relationship conjugates, or complex conjugates. I'm just going to call them conjugates. This number is the conjugate of this one is the conjugate of this one. We say that they are conjugates. So something interesting happens when you multiply two complex conjugates together. If I were to FOIL this, I'm going to have 3 times 3, which is 3 squared, that's 9. 3 times -7I, which is minus 21I. 3 times 7I, which is plus 21I. And then 7I times -7I, that's minus 49I squared. Okay. One thing you'll notice is that the i's, the -27I and the plus 27I, those are going to cancel out. So the only thing I'm left with are real numbers. Secondly, when this I squared becomes a -1, it'll change this -49 into a positive 49. Okay, now I'm going to add those up, but before I do that, two things, again, worth reiterating about this. One, the i's canceled out, like we said. We're left with only a real number. Secondly, the real number that we're getting here is just the sum of the squares of the real and imaginary parts of either of these. So 3 squared plus 7 squared. That's what we're getting. This always happens when you multiply two complex conjugates together. We get 58 in this case. Knowing that is useful because, as we're going to see in division with complex numbers, what we're typically trying to do is get the number that we're dividing by, the divisor, to look like a real number. And you can always create a real number from a complex number by multiplying it to its conjugate. It always comes out real. Secondly, if we know this trick where the product of these two numbers is just the sum of the squares of the real and imaginary parts, we can mentally do this multiplication without going through these steps here. So let's move on to division and see see what division looks like. So, okay. Let's suppose first of all that I wanted to divide, let's say 3 minus 2I divided by 4I. This is kind of the simpler case where there's not a whole lot that we actually need to worry about. But for this, what I'm going to do is I'm not going to do division directly. It's not going to look like a long division problem. Really, the first goal is just to eliminate the I in the denominator somehow. And we don't cancel it with anything. Instead, what we do is we multiply by something that's going to cause this number down here to become a real number. There's different options, but the simplest one is to multiply this one by I over I. Now notice if I were to distribute this I in, I'm going to get 3I minus 2I squared up in my numerator over 4i squared when I multiply the denominators together. The goal now is going to be to simplify the I squareds. In the definition of a complex number, this is kind of just a matter of convention. A plus bi, the real part always comes first, followed by the imaginary part. So I'm going to try and keep that convention. As soon as I multiply or do the math on this, negative 2i squared is going to become positive 2, but I'm going to put that first. So it becomes 2 plus 3i up on top over I squared is negative 1, so 4i squared will become negative 4. Okay? Now the next thing I want to do is separate this into a sum of two fractions. This is equal to 2 over negative 4 plus 3i over negative 4. Okay? I'm going to simplify these fractions now. This becomes negative 1/2. This becomes minus 3/4. And the I that's in the numerator can be brought out to the front of the fraction. Notice that what I just did, and it's basically from simplifying this, I've managed to take this division problem and just kind of algebraically simplify it until it turned into something of the form A plus BI. That's the goal, is you're trying to determine what does this look like as a complex number. Okay, let me try that with an example where the denominator is a tad more complicated looking, just a little bit. So let's try this. 4 minus I over, let's say, 2 plus 5i, something like this. Okay, if I just multiply this by an I over I, like I did in the previous example, even though this I will become a negative 1 and make this a real number, I'm going to get a 2i here, so I haven't really fixed the problem. Instead, we're going to use what we talked about with multiplication and multiply. That should be a multiplication, not an equals. We're going to multiply by the conjugate of the denominator. So instead of 2 plus 5i, I multiply by 2 minus 5i. Okay? Now, we know what's going to happen in the denominator. We came up with a shortcut. The result is going to be the sum of the squares of the real and imaginary parts, 2 squared plus 5 squared, or 4 plus 25, which is 29. In the numerator, I'm just going to FOIL that. So I'm going to get 4 times 2, make this a little bit bigger, which is 8. And then I'm going to get 4 times negative 5i, so that's minus 20i. Then I'm going to get a negative 2i, and then finally a negative I times a negative 5i, which is positive 5i squared. Okay? So I know that this 5i squared will become a negative 5. Adding the 8 to that gives me a 3. I have negative 20i minus 2i. This will become negative 22i over 29. Okay, it's a little bit sloppy, sorry about that. And then, just like the previous example, we split this into two fractions, which in this case there's no simplifying to do, and then bring the I out of the second fraction. So this becomes 3 over 29 minus 22i. Whoops. Over 29. Bring this I out like this. That'll be our final answer there. Okay. In the next video, we're going to look at what happens if we take higher powers of I, and then we're going to look at some very basic algebra with complex numbers.